Okay, so now let's see two examples. So first example, we have the matrix A, 2 by 2 matrix, 2, 1, negative 3, 1. Okay, and our question is that we want to apply, we have two questions. First one, we want to apply Guan-Xu-Mi. Guan-Xu-Mi process is this one, Guan-Xu-Mi. Guan-Xu-Mi process. Guan-Xu-Mi process. Guan-Xu-Mi method. To change these two vectors. Here we have two vectors. First one is 2, 1. And here the matrix A just combine these two vectors. 2, 1 and negative 3, 1 into an orthonormal basis. An orthonormal basis. U1, U2, U1, U2 of R2. Just originally we have two vectors, and it's not difficult to see that they are linearly independent, and we could change it into an orthonormal basis U1, U2. And of course, we should use the Guan-Xu-Mi method. Use Guan-Xu-Mi method. And the second one is, let me see. Second one is the method. If I denote the matrix Q by this one, U1, U2, then we could show that Q is orthogonal. Q is orthogonal matrix. Orthogonal matrix. It's the second result. Second one. And the second one is easy to see. Actually, orthogonal matrix means that Q transpose Q equals identity. And as we know, U1, U2 are orthonormal basis. So second one is easy to see. But later I will write it down again. Yeah. Anyway, so first one. So here just follow the process, and here we just two vectors. So I think for this example, just follow. We just have the first one, second one, and the three. First step, second step, and the third step, and we solve it. So here we could denote it by S1, S2. Of course, you could start from this vector. We could denote it by S1, S2. It's also fine, but I just start from this vector. Yeah. But originally, of course, the first step is that it's easy to check. If you check 2, 1, negative 3, 1, determinant is 2 subtract negative 3 times 1. 2 times 1 subtract negative 3 times 1. So it's 2 plus 3. So it's 5. It's non-zero. So this matrix is determinant non-zero, means that these two vectors are linearly independent. So it means that they are linearly independent. So if they are linearly independent, probably they are orthogonal. They are not orthogonal, and we could use the Guan-Xu-Mi method to find orthogonal moreover or orthonormal basis. Yeah. Okay. So the first step, we denote S1 by 2, 1, S2 by negative 3, 1, and we use we have 3 steps, right? We have 3 steps. Okay, so it's our first question. The first step, our U1 is divided by its length. So for U1, we should divide by its length. So of course we should figure out its length. So x1 its length equals square root of sum of the square, square root of 5. So first step, U1 is divided by its length. So it's 1 over square root of 5 negative 3, 2, 1. this one, u1, this vector, this way, and of course it's this one, divided by square root of 5, divided by square root of 5, this vector. So it's our first vector, u1. And second vector, u2. u2, first of all, second step, you should derive p1, projection of s2 onto s1. So p1, the formula is u2, sorry, s2. You consider vector s2 and consider u1. Our formula is x2, u1, their inner product times u1. The inner product times u1. So it's x2 is the vector negative 3, 1. u1 is this one. So it's, but we should, yeah, u1 is this one. 2 square root of 5, 1 square root over 1 of square root of 5. The inner product times the vector 2 over square root of 5, 1 over square root of 5. This one. This one. Okay, and what's the inner product? Negative 3 times 2 over square root of 5, so it is negative 6 over square root of 5 plus 1 over square root of 5 times the vector 2 over square root of 5, 1 over square root of 5. This one. But this one subtract 6 plus 1, so it's subtract 5 over square root of 5. Okay, but 5 is equal to square root of 5 is square, so it's equal to subtract square root of 5. This 10 is exactly this one. Exactly subtract square root of 5. So this 10 is, this one is exactly this one. So this scalar multiplied by this vector, then you could cancel it. For the denominator, we could cancel it. So it becomes negative 2, negative 1. Negative 2, negative 1. Negative 2, negative 1. And then it's our vector projection P1. P1 is our projection of S2 onto S1. Projection of S2 onto is our projection. It's the projection of S2 onto S1. Onto S1. It's the second step. And the third step, just divide by its length. U2, just divide by its length. And sorry, S2 subtract P1, divide by its length. Yeah, divide by its length. So S2 subtract P1, so first of all, so what's the S2 subtract P1? S2 is this one, P1 is this one. So first of all, you should figure out S2 subtract P1. S2 subtract P1 is negative 3 subtract negative 2. 1 subtract negative 1. So it's plus 2, so it's negative 1. Plus 1, so it's 2. So it's negative 1, 2. Negative 1, 2. This vector. This vector. And its length is square, so its length, so we should divide by its length. So its length is negative 1 is square, 1. Plus 2 is square, 4. Multiplied by this vector, negative 1, 2. So finally, the vector is, here 1 plus 4 is 5. So finally, and we use distribution, so finally it's negative 1 over square root of 5. 2 over square root of 5. Sorry. Yeah. Do you see that? Yeah. Do you see that? Okay. 2 over square root of 5. 2 over square root of 5. This one. 2 over square root of 5. Here is 2. Here is the numerator is 2. This one. Okay, negative 1, 2. This one. So S2 subtract P1 in this vector. Oh, sorry, no. It's our U2. Okay. It's our U2 in this vector. So U1 is this vector. U2 is this vector. Okay, so first of all, first question, U1 orthogonal basis. U1, so U1, U2 is, vector U1, U2 is 2 over square root of 5, 1 over square root of 5, and negative 1 over square root of 5, 2 over square root of 5. Yeah, these two vectors. Okay. And the second question, Q is orthogonal matrix, and here is our U1, is our U2. So for second question, you could check it directly. As here, since we will use this formula again, so I just keep it. So now I use this one. So second question, there are two ways to explain it. First one, you could say that Q. Actually, first one you could check it directly. Q is the matrix U1, U2, as we say. U1, U2. So Q is the matrix. U1 is 2 over square root of 5. Negative 1 over square root of 5. 1 over square root of 5. 2 over square root of 5. It's a matrix. Negative 1 is over here. And here is 1. This one. So now Q transpose. We want to show this one. Orthogonal means Q transpose Q equals identity. So Q transpose becomes 2 over square root of 5, and first row becomes first column, negative 1 over square root of 5, 1 over square root of 5, 2 over square root of 5. So you could really check this one just by definition. You could see that it's equal to 4 over 5 plus 1 over 5, and sub negative 2 over square root of 5 plus 2 over square root of 5. And here is negative 2 over square root of 5 plus 2 over square root of 5. And the last one, negative 1, positive 1 square root of 5 plus 4 over square root of 5. So it becomes 5. Here. Let me see. Oh yeah, all of them, the denominator is 5. Sorry. All of them, the denominator is 5. The denominator are 5. Anyway, it's 0, it's 5 over 5, so it's 1. 5 over 5 is 1. So indeed, 1, 0, 0, 1. So indeed it's equal to identity. 1, 0, 0, 1. 1, 0, 0. So indeed, we have this one. Yeah. And the second one, if we want to show that Q is orthogonal matrix, just use the result in previous section. I mean, since U1, U2 are orthonormal, since they are orthonormal bases of R2, then we know that by previous result we know that Q the matrix Q U1, U2 is orthogonal matrix. They are orthogonal matrix. Yeah, so just the reason is that Q is orthogonal, and the reason is that the result in first question. So just write down the reason, then you could write down the solution directly. Okay, so it's these two questions. It's the problem about these two questions. But it's 2 by 2 case. So even for another 2 by 2 case, you could use the similar argument. But we have not talked about this case, because if just two vectors in R2 space, we just need to consider projection of S2 onto S1. So we don't need to consider P2. So now I will give you 3 by 3 case. Then you should consider P1, and you also need to consider P2. It will be a little complicated compared with this example. Yeah. Okay, and it's our final example. Yeah. And I have some homework problem, I mean you could check it by yourself. Okay. So I will use this argument, so I still keep it. Yeah, so I erase this part. Okay, so now second quick example. We have the matrix. Now it's 3 by 3, so we consider 2, 1, 2, 1, 1, 1, 1, 1, 0. And so we still apply Gram-Schmidt. The process is called Gram-Schmidt or Gram-Schmidt method. Gram-Schmidt process to change these three vectors 2, 1, 2, 1, 1, 1, 1, 1, 0 to change 2, 1, 2. 1, 1, 1, 1, 1, 0 into also normal and also normal basis of R3 and also basis we call U1, U2, U3. And of course you could say ignore the matrix Q by U1, U2, U3, and you could say that in the previous result we know that this matrix Q is orthogonal matrix. Okay, so we just can, but so for this part we could skip it. We focus on this question. Okay, yeah. And now let's see how to solve it. The solution. So now we have three vectors. It's our x1, x2, x3. So we denote it by s1 is 2, 1, 2, s2 is 1, 1, 1, s3 is 1, 1, 0. And then you still could check its determinant. I mean, this matrix A is determinant, and you could see that its determinant is non-zero. So you could see that indeed they are linearly independent. Okay, they are linearly independent. And if they are linearly independent, you could see that you could use the Gram-Schmidt method to construct the orthonormal basis. Okay, and by the way, if we have two vectors, s1 and s2, and if two vectors, just by the way, if we have two vectors, s1, s2, and if they are linearly dependent, then if we use the projection formula of projection, what will you get? Here P1 is S1, S2, S1 divided by its length times S1 divided by its length, right? And if S1 and S2 are linearly dependent, for example, S2 equals alpha times S1 for some non-zero alpha, it's a linear dependent, so S1 is a multiple of S2. S2 is a multiple of S1. So we assume S2 equals alpha times S1. So here, what's this? This one is, here S2 is alpha times S1. S1 divided by its length. And what's this? It's alpha take out and S1 is length take out, and S1 is length. But this part, inner product, is exactly S1 is length squared. So it's cancel length. So finally it's alpha times x1. But alpha times x1 is exactly x2. right? So if these two vectors are linear dependent and you put the projection of S2 onto S1, you will get it's exactly S2. And what does it mean? It means that we have a vector S1 and S2 is a multiple of S1, so probably S2, and they are linear dependent means we could put it in the same direction, in the same line. I mean S2 is over here, it's equal to alpha times S1. And its projection, of course, its projection is exactly equal to itself, right? It's exactly equal to itself. Okay, so in the formula, if they are linear dependent, you will get P1 is exactly just equal to X2, just equal to X2. Okay, yeah. Okay, so just to remind you, yeah, in linear dependent case. Anyway, so now it's linearly independent. We could use the formula, and we use the formula. So we have 5 steps. So our first step, we consider it step by step. So first one, okay, so first step, our U1 is S1 divided by its length. So in our first step, we should consider S1 is length. S1 is length is square root of sum of each term. 2 square plus 1 square plus 2 square. So it's 4, 1, 4. So 4 plus 1 plus 4 is 9. Square root becomes 3. So U1 is the vector S1 divided by its length. So it's the vector divided by 3. So each term we divide by 3. So 2 divided by 3. 1 divided by 3. 2 divided by 3. This one. Okay, yeah. Or this term, since we use this formula, so it's 1 over 3 times S2. S2, this vector. Okay, yeah. S1 divided by its length. So it's 1 over 3. So it's 1 over 3 times x1. 1 over 3 times s1. So it's this one. Okay, and the second step. It's the first step. And second step is figure out the projection of S2 onto S1. The projection of S2 onto S1. So P1 is S2. We use the formula S2 U1. So it's X2 is 1, 1, 1. U1 is 2 over 3, 1 over 3, 2 over 3. The inner product times 2 over 3, 1 over 3, 2 over 3. And here, what's the inner product? The product entry-wise multiplication. So 1 times 2 over 3, so 2 over 3 plus 1 over 3 plus 2 over 3 times this vector, U1. So here is 2 plus 1 plus 2 is 5 over 3. 5 over 3, so we should multiply by 5 over 3 in each 10. So it becomes 10 over 9, 5 over 9, 10 over 9, 10 over 9. This one. So it's our vector projection of P1. But third step is U2. So you should consider S2 subtract P1 and divide by its length. So S2 subtract P1 is equal to subtract P1. 1 subtract 10 over 9, so it's negative 1 over 9. 1 subtract 5 over 4, so 5 over 9, so it's 4 over 9. 1 subtract 10 over 9, so it's negative 1 over 9. This one. So the vector U2 is S2 subtract P1 divided by S2 subtract P1 is length. So you should figure out its length firstly. So first of all, we consider its length. S2 subtract P1. What is its length? Square root of negative 1 over 9 is square, so it's 1 over 81 plus 16 over 81 plus 1 over 81. This one. So is equal to 16, 17, 18, 81. So we divide by 9 both simultaneously, so it's 2, 9, so it becomes square root of 2 over 3, square root of 2 over 3. Yeah, so what's the vector? S2 sub U2. U2 is the vector, so U2 is the vector x2 subtract p1 divided by s2 subtract p1, its length. So it's s2 subtract p1, its length, for its length, its reciprocal times s2 subtract p1, this vector. So its reciprocal is 3 over square root of 2 times the vector s2 subtract p1. Let's still keep it s2 subtract p1. And finally, we could write down each 10. So for first 10, we multiply 3 over square root of 2. So we still have -1, -3. Let me see. For this 10, we cancel the 3, 9, so you still have -1. 9 divided by 3 becomes 3. 3 square root times square root of 2. Second 10, you divide by 3, so you have 4 over 3 times square root of 2. The last one, divided by 3, -1 divided by 3 over square root of 2. This one. Okay, so it's vector U2. And finally we have it's the first state, second state, the third state. It's the third state U2. But we should figure out U3, so P2 U3. So P2 U3, our formula is this one. So I erase this part. I erase this part and keep the formula. So now let's see the final two steps. Okay, the fourth step. P2 is this one. So now P2 is defined by S3 U1 because P2 is the projection of S3 onto S1 S2, onto span of S1 S2, and it also means onto span of U1 U2. So it's span onto span of U1 U2. So you could write down in this way. S3 U2 inner product times U2. Okay, so our vector S3 is this one. So you should figure out S3 and the U1 is this one, the inner product. So S3 is 1, 1, 0, 2 over 3, 1 over 3, 2 over 3. Its inner product times 2 over 3, 1 over 3, 2 over 3, plus S3 1, 1, 0. U2, what's the vector U2? U2 is this guy. -1, 3 over square root of 2, 4 over 3 square root of 2, -1 over 3 square root of 2, this one. The inner product times this vector. -1, 3 over square root of -1 over 3 square root of 2, 4 over 3 square root of 2, -1 over 3 square root of 2. What's this? Inner product. So 1 times 2 over 3 plus 1 times, yeah, so it's 1. So here I write down each 10. 2 over 3 plus 1 over 3 times U1. This vector we call U1 plus -1 over 3 square root of 2 plus 4 over 3 square root of 2 times U2. This vector is U2. And here becomes 1. So it's the vector U1. Here is 4 subtract 1, so it's 3. 3 divided by 3 square root of 2, so it becomes 1 over square root of 2. 1 over square root of 2. So the first vector in U1 is this one. So it's 2 over 3, 1 over 3, 2 over 3. Plus 1 over square root of 2 times this vector. So what's this? First 10. it becomes negative 1 square root of 2 square root of 2 times 3, so it's 6. Second term, it becomes 4. Second term, 1 over square root of 2 times 4 times 3 square root of 2. So it's 4, 3 times 2. But 2 we could cancel then. So I mean 2 divided by 2, so you still have 2. So it's 2 over 3. 2 over 3. Then the last 10, negative 1 over 3 times 2, 6. This 10. And so finally the vector is this one. And here just computation, so I erase this part. Erase this part. And they make a common denominator, so it's 4 over 6, 2 over 6. For this vector, 2 over 6, 4 over 6. So their combination, their sum becomes 4 sums to 1, 3 over 6. Here is 4 over 6. Oh, 1 over 3, 2 over 3 is 1. And here is 3 over 6. It's exactly 1 half. 1 half. The vector is exactly. So the vector P2 is exactly this one. And the P2 is the projection of S3 onto span S1, S2. Yeah. And finally, we should consider the U3, just S3 subtract P3, P2. Oh, sorry. Okay, here. Sorry. This one we should mention correctly. Sorry. We should correct it. It's P2. It's P2. Yeah, so this part, sorry, this part I should correct it. This part I should correct it. Okay, so the final step. It's our final step. And I write down here. It's our final step. And this one we call it is the projection of S2, S3, onto span cell of S1, S2. And the final step. First step, just we should consider S3 subtract P2 firstly. So S3 is this one, 1, 1, 0. P2 is this one, 1 half, 1 half. Let me check it. Yeah. So it becomes 1 sum to 1 half, 1 half, 1 sum to 1, 0. 0 sum to negative 1 half, so it's negative this one. And so we should divide by its length. So we should know its length. I mean S3 subtract P2. Its length is square root of 1 half is square, so it's 1 over 4. Plus 0 plus negative 1 half is square, so it's 1 over 4. So it still equals 2 over 4, so it's 1 half. So its square root is 1 over square root of 2, this one. So finally, U3 is S3 subtract P2 divided by its length. Divided by its length, so it's square root of 2 times 1 half, 0, 1 half, negative 1 half. So finally, the vector U3 is 1 over 2 times square root of 2, 0. Negative 1 over 2 times square root of 2. This vector. Let me check. Oh, sorry, it's reciprocal. Sorry, there is something wrong. Here the length is, we put the length in denominator, so we should consider it's reciprocal. So here is square root of 2. Sorry. Yeah, so it's indeed it's a little complicated. Yeah. So it's reciprocal, so it's square root of 2 times this guy. So it's square root of 2 over 2, 0, negative square root of 2 over 2, this one. And of course, yeah, just this time. So now you have 3 vectors. You have 3 vectors. U1 is this one, and the U2 is this one. U2 is this one, and the U3 is this one. So I mean U1, U2, U3 is what we want. It's orthonormal basis. Orthonormal basis of R3. And it's all the material in this section. It's all the material in this section. Yeah, and this here I write down I could give you the homework problem section 5.6. You could check the problem 1, 5A and 6A. This one for this section. Yeah, and if I'm not sure, right? Have I given you the homework in section 5.5? If I haven't given you the homework problem, I could give you now 2A, 4A, 21. Yeah. And still giving. I could still give you the homework section 5.3. It's 1B, 2A, 3A, 5A. Okay, that's all. Yeah, that's all the material in chapter 5.